YMP students play an integral role in the development of various products from Rockwell. Christopher Brooks from the MCT process line with co-worker Justin Walker, as well as Christine Liu from Materials Processing and Chemistry and Jeremy Lau from Electromagnetics, are inspecting an early stage of a mercury-cadmium telluride infrared device, which will later be integrated into an infrared system. Christopher's advisor in this activity is Gary Bostrup. The 21 square objects on this 3-inch wafer are actually individual arrays made up of over 65,000 separate pixels. Each array is designed to see a particular wavelength of infrared light and sized to be mated with a silicon integrated circuit. As part of the process, each wafer goes through a complete testing procedure which verifies whether or not the infrared arrays meet specifications. Here Chris is putting the wafer in the cryoprobing machine. With the aid of this machine, test devices are first cooled to their operating temperature of 77 degrees above absolute zero. Due to this ultra-low temperature, proper test conditions demand the mercury-cadmium telluride arrays be kept in a high vacuum. After the cryoprobe machine is sealed and all the internal air is pumped out, the proper adjustments can be made via the linked electronic equipment. While under vacuum, Chris must take extreme care and bring metal probes the size of a human hair in contact with the test devices. From here, a computer linked to the cryoprobe machine systematically interrogates each device and evaluates the overall quality. Special software developed by our YMP students also helps to ease the use of test equipment and aid device result interpretation. Nicholas Laird explains to Harvey Shea from Diagnostics and Modeling and Alex Robinson from Distributed Systems and Communications the work he has done as a YMP intern. At the Science Center Power Electronics Lab, Nick has been helpful in lab test setup and documentation for an AC to AC power control project. This is a schematic drawing of a test circuit Nick did using Visual Technical software. The test circuit for AC semiconductor power switches has been implemented and is now under testing. Here Nick with his advisor, Jay Chang, show Harvey and Tim the actual hardware and discuss the test results observed on this 4-channel oscilloscope. The green and turquoise waves show the voltage waves crossing the AC switches. The white wave shows the current waves. AC to AC converter circuits can be used in various industrial and aerospace applications, such as electrical motor controls and actuators. Eric Cheng from Interfacial Processes has been working with his advisor, Martin Kindig, on identifying corrosion inhibitors that will inhibit galvanic corrosion produced by small defects in otherwise passive metal surfaces. Here Eric is showing a sample to fellow YMP students Vicki Chung and Jane Kim, also in the Interfacial Processes department, and Meredith Pappas from Structural Ceramics. Eric determines the galvanic current flowing between a small iron electrode and a large zinc surface. This system simulates a defect in a galvanized coating on steel. The solution the sample is put in is sodium chloride, similar to salt water, which also contains some chromate inhibitor. Rockwell Automotive uses such materials to manufacture many components. Similar types of galvanic effects have been observed as a result of intermetallic phases present on high-strength aluminum alloys used in the aerospace industry. The rapid electroanalytical technique used by Eric to directly measure galvanic corrosion in such systems will help us to identify new corrosion inhibitors for a variety of applications. This effort becomes important in light of the desire by Rockwell to replace hazardous chromate inhibitors with more environmentally benign compounds. Ron Scrofano from High Speed Materials and Devices and his advisor Wei Hing Chang discussed the work Ron has been doing as a YMP. Ron has created schematic drawings for circuits designed by Wei Hing. Here they are comparing a previous printout to a new simulation on the computer screen. These circuits are made up of two-dimensional memory arrays which have 1,024 cells. Lee Kwok, James Lowe, and Jeff Chang, all in the high-speed circuits department, look on as Ron explains the circuit schematics he has designed. Ron created these schematics using a Windows-based schematic capture PC program. The result of this work will provide faster computer memory, perhaps 10 times faster than today's computer memory. Kyla Brook and Sarah Wong from the compensator process line discuss with Jasmine Tai, also in their department, and co-worker Michelle Lee the work they have been doing during their internship. Kyla mounts an organic compensator and secures it on the plastic holder. Organic compensators are thin film devices designed to enhance the performance of liquid crystal displays. They are typically fabricated on glass substrates. Sarah loads the compensator on the ellipsometer, which will measure the characteristics of the compensator. A laser goes through the compensator as it rotates to various angles. An analyzer then collects the data, and it is displayed and stored on the computer. Jasmine has analyzed compensator measurements for statistical trends. This data is used to characterize the compensator fabrication process and deduce such properties as process yield and the capability of the process to meet customer requirements. Brian Stevenson from Control and Power Technology has been working with his advisor, Dan Rogovin, as well as Martin Kindig from Interfacial Processes. Brian has participated in a project supported by Rockwell Automation to develop diagnostic techniques for AC electric motors. Brian explains to YMP interns Tricia Sando and Amber Sands from Design and Reliability and Bud Raymond from Structural Ceramics the testing he has been doing. Here Brian measures the broad frequency impedance of the stator wiring of a motor using a network analyzer. The measurements are made as the motor undergoes thermal degradation in the oven. This simulates one of the motor's failure modes. Results from Brian's experiments have allowed us to gain a better understanding of the mechanism of failure for AC motors. Mark Appleford from Structural Metals, with advisor Jonathan Flintoff, show the testing Mark has been doing during his internship to fellow YMP students Mickey Hassenfratz from Distributed Systems and Communications, Tim Vanderhorst from Imaging Devices, and Thomas Warren from Optical Devices. Mark has conducted a series of experiments to determine the burst pressures of square cross-section polymer tubular elements. Here Mark has already fitted, adhesively bonded, and clamped a specimen into a test fixture. He lowers the sample into a large dewar and decreases the test temperature by pouring liquid nitrogen over the sample. Using a gas pressure regulator, the pressure is slowly increased until the tube walls burst. The burst pressure is autographically recorded from a pressure transducer and readout electronics that are in line with the pressurized gas. This close-up of the sample shows the entire specimen is burst, leaving the large part of the center of the specimen completely blown apart. This is because the polymer becomes very brittle at such low temperatures. Another test Mark worked on was tension testing of metals. Mark shows a sample of a new steel that will be used in automobile wheels. This sample is placed in a servo-hydraulic test machine. An extensometer measures axial elongation of the sample. The actual test consists of pulling the sample apart at a specified rate and recording the elongation and load as the sample is stretched to failure. As the sample is being tested, a computer plots the process. Here you can see the load or stress increase on the vertical axis of the plot as the elongation or strain increases on the horizontal axis. These test results will be used to provide engineering material properties such as strength and ductility that will be compared with other types of steels. This in turn will yield a determination of how the steel can be formed into a wheel and how much better it may be for making these components.